Chapter 6, Section 1 is the title about electricity from magnetism. Before starting this section, we should remember some information about electric current. So, electric current is provided by a battery. Battery is a DC, direct current source. A battery has a positive terminal and a negative terminal. When you connect a device, for example a bulb, between the terminals of this battery, so electric current starts flow from positive to negative. So the positive end of the battery is high electric potential. Yeah, this terminal, which is positive, has high electric potential, and negative terminal of the battery has a low electric potential. So when you connect the bulb between these two terminals, so electric current starts moving, flowing from a positive terminal through the bulb and to negative terminal. So electric current flows from positive end or terminal of the battery to the negative end or the terminal of the battery through the bulb or the lamp. So the bulb gives light. So the battery is the source that supplies electrical energy. Right here, the battery is the source which supplies electrical energy. And any device that supplies electrical energy is called source of electromotive force. So any device which supplies electrical energy is called source of electromotive force, source of electrical energy. So this force, the term force here does not refer to as usual force concept. This is in fact completely related to potential difference. A battery is the only source of electromotive force. Till now, yes, you will learn on the batteries, only DC sources, but it is also possible to induce electric current or to produce electric current by using some techniques of electromagnetism. When we say induce, you are going to understand it means produce. Now, before starting this section, I'm going to remind you some information about this chapter 5, and we are going to explain this section on the information which is given in the previous section. It was this: if a current carrying lobe is located inside a magnetic field, for example, this is the N pole, that is the S pole, and from N to S there is the magnetic field. And if you locate a wire between these poles and inside the magnetic field, and if there is no current given on the wire on the conductor, so there will be no magnetic force acting on the wire. But if electric current is given through this wire, in this case there will be a magnetic force acting on this wire. Right here, the magnetic field direction is into the page. Electric current direction is up to the plane of the page. So according to right hand rule, so you can understand that the palm is the force acting on the wire. For that reason, this wire will be pulled in negative x direction with a magnetic force. So right here, the electric current inside a magnetic field results a force and move the conductor to the left. So now we ask a question: if the process is reversed, yani if a conductor is moved perpendicularly in a magnetic field, what will happen? So as you see here, a conductor is pulled. So you are going to pull it with your hand or with any external force. So while a conductor is being pulled inside a magnetic field, the electrons are also pulled with the conductor. Remember, on a conductor there are free electrons. Electrons are free to move. Protons are at the nucleus, but electrons are free to move. When you pull the conductor, the electrons also moving with the conductor from left to right, and in that direction. So the moved electrons to the right experience a magnetic force downward. How? Because according to right hand rule, magnetic field is into the page. So this is the direction of the motion of the electrons on your conductor. So electrons will accumulate in the opposite of your palm. Yani in this, at the bottom end of the conductor, electrons will accumulate. So upper end of the conductor will be positively charged because electrons will leave here and then go there. So the moved electrons to the right experience a magnetic force downward and accumulate at one end of the conductor. This end becomes negatively charged as you see here. But if you change the direction of the motion of the conductor, in this case, electrons will accumulate on the upper end. If the direction of the motion of the conductor is reversed, the electrons will pushed upward, so the polarization of the conductor will change. And initially it is positive, negative. So if you pull the conductor in opposite direction, it will be negative, positive. So then, if the conductor is connected to a device, now this is a conductor pulled inside a magnetic field with a speed v. If we connect this device to a lamp, for example, it is possible to give this light this bulb light, because electric current starts flowing from positive terminal to negative terminal to the bulb, and bulb starts giving light. So then, if this conductor is connected to a device, it supplies an electric current called induced current. Now, these types of electrical energy production, in this type of electric energy production, we say the current supplied to the circuit as induced current. Induced electric current by using magnetic field is called electromagnetic induction. The induced electromotive force E, so the electromotive force or potential difference between these two ends, say E, depends on strength of the magnetic field 1. So if no magnetic field, of course you cannot apply a force on the charged particles. Charged particles cannot move through the conductor. There will be no polarization of negative and positive. Second, you should pull the conductor, V. No V, no magnetic force again on the charged particles. Of course, they will not move. Of course, length of the conductor, because if the length is longer, so then there will be many free electrons. So then the electrons will accumulate. More electrons will accumulate on the lower end, so positive upper end will be charged positively in a greater amount. So then if you multiply these three quantities, B times V times L, we are going to get the equation for calculating induced EMF for a conductor which is pulled inside a magnetic field. So here is key information is that when you are pulling the conductor, you should cross the magnetic field lines. If the conductor crosses the magnetic field lines, so in this case there will be induced EMF or induced current on this conductor. But if the conductor is moving parallel to the magnetic field lines, so there will be no force acting on the charged particles, there will be no induced EMF. If you pull the conductor with an angle to the magnetic field lines, just you are going to substitute, add here sine theta, and you can calculate the induced EMF again. So inducing electromotive force by moving a straight conductor in a magnetic field is one of the methods of electromagnetic induction. Now the second method. Second method is the inducing electromotive force by moving or in a loop, in a wire or in a coil. So this is a loop, as you see here. So a magnet with N pole and S pole. So then when we move this magnet towards this loop, it will be observed that on this loop there will be induced some current. So it is possible to get this by using a very simple galvanometer. You are going to connect the loop and you are going to observe that. So what's happening here when you move this magnet and loop closer relative to each other? So now if you count the number of lines crossing this area, which is in fact the magnetic flux, you will see that 1, 2, 3, 4, 5 lines crosses the loop area. So right here, if we say magnetic flux is 5 Weber, in this case, another case, when the magnet approaches to the loop, in this case magnetic flux number of magnetic field lines crossing the area increases 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So magnetic flux right now is 11 Weber. So what happened? Magnetic flux increased from 5 to 11. So then, in general, we can say that if you change the magnetic flux through the loop, so in this case there will be an induced current in the loop. And this is the key information. You should change the magnetic flux crossing the loop or the coil. So then you are going to induce a current on the coil, induced EMF. So you can change the magnetic flux by increasing or by decreasing. So this is the equation for magnetic flux. Magnetic flux is equal to area of the loop multiplied by magnetic field through the loop multiplied by cosine theta. Theta is the orientation of the loop. Yani we can change the magnetic flux by three ways. By changing the area of the loop, by changing the magnetic field through the loop, or by changing the orientation of the loop with respect to the magnetic field. So the first one, in fact, I defined by changing the magnetic field strength B through the loop. How can we change the magnetic field? We can make the magnet approaching to the loop, so we can increase the magnetic field. So to do that, move a bar magnet. So in this case, the loop will be somewhere here, closer. So the number of the magnetic field lines crossing the loop increases. So to do that, move a bar magnet towards or away from the coil. If towards, magnetic flux increases. Away, magnetic flux decreases. This is the first way. Second way is change the area of the loop through which magnetic field line passes. Now look at here. In the first position, the area which is inside the magnetic field is very small, as you see. Only 2 lines crosses the area. So magnetic flux is 0. But as the loop enters inside the magnetic field, the area which is inside the magnetic field increases. So then magnetic flux and number of magnetic field lines crossing the area also increases. So to do that, move the loop into or out of the magnetic field region. And third one, change the angle theta between the normal of the surface and magnetic field lines. Yani you are going to change the orientation of the loop. This is the coil or the loop. So many loops are there. So normal of the surface is this. Any angle which is perpendicular to the surface is called normal of the surface. As you see, angle between the magnetic field lines and the normal of the surface is that angle. Then you rotate the loop in clockwise direction. Normal is now, this one is normal, and the angle between the magnetic field lines and the magnetic flux increases. So in the first case, there are 1, 2, 3, 4, 5, 6 lines crosses the area, but in the second position, no magnetic flux crosses this area. So in this case, magnetic flux will decrease. To do that, rotate the coil inside the magnetic field. As you see, when you are rotating the coil inside the magnetic field, it is also possible to change the magnetic flux by changing the angle. So this is a ministry exam question. Which of the following ways can induce a current inside a closed circular loop? Ministry question 2015. By moving the coil loop in or out of the magnetic field, so changing the area. There is a change in the area which is inside the magnetic field. By changing the magnetic field strength or its direction around the loop, so change in the magnetic field. So direction also can be changed because area and the magnetic field is a vector quantity. C, by rotating the loop inside the magnetic field, this case is defined. So by rotating the loop inside the magnetic field, you can also change the magnetic flux, induce electromotive force. So answer is all of them. So now, of course, when you remove a magnet closer and away from a coil or a solenoid, so on this solenoid there will be an induced current, and this induced current will result an induced magnetic field on this solenoid. So how can we find the direction of induced magnetic field and induced current? There's a very simple rule or practical way for finding the direction of the induced magnetic field. If a bar magnet approaches to the solenoid, if N pole is approaching towards the solenoid, the facing end of the solenoid will be N. Yani N will face N, and that will be S. If S pole of the permanent magnet approaches the solenoid, in this case, facing end of the solenoid will be S. S and S faces each other, and an S faces each other in the case of approaching. And if these two, solenoid and the magnet, approaches relatively each other, so in this case, the poles will be N and N, or S and S. So according to that, you can find the direction of the electric current on this by using right hand rule. We are going to do it later. But if the N pole of the permanent magnet moves away from the solenoid, or S pole moves away, in this case, solenoid will make a magnetic field so that N pole of the permanent magnet will face S pole, or S pole of the permanent magnet will face N pole, and unlike poles will face each other. So if this is S, that will be N. If this is N, that will be S. So according to this, now we can find the direction of the electric current on the solenoid. For example, assume N is receding away, or moving away from the solenoid. The permanent magnet is moving away from the solenoid so that N pole faces the solenoid. In this case, this will be S, that will be N. Then we are going to use the right hand rule. So thumb must point the direction of the N pole of the solenoid. Curled forefinger is the electric current direction on the loop. So in this case, electric current direction will be like that on the loop of the coil solenoid. Then follow the line, so it must follow this way, or go on like this, down. So electric current direction will be from left to right on the resistor located here. So if S pole recedes from the solenoid, in this case, the facing end will be N, and will be N, S, N, so that is S. This time, thumb must point the N pole. The curled forefinger will be the direction of the electric current on the loop of the coil or the solenoid. So now in this direction of the electric current on the loop of the solenoid will be like this. So follow the wire and you are going to understand that electric current on the resistor will be from right to left. Now let's do for the case approaching. If S pole, or if the magnet approaches to the solenoid so that S pole faces the solenoid, so this, if this is S, that will be S. In this case, that will be N. So then again, thumb must point in the direction of the electric current. So four fingers curl in the direction of the electric current on the solenoid. So this will be the direction of the electric current on the solenoid turns. So then from, if you follow the circuit, it will be from left to right on the resistor. This is the practical way for finding the induced current on a solenoid, but in fact scientifically we can find it by using Lenz's law. The rule finding the direction of the induced current is called Lenz's law, and it's expressed as follows. The magnetic field of the induced current, in fact, we set this induced current magnetic field as induced magnetic field, is in a direction to produce a field that opposes the change, opposing the change, causing it. Like what? What causes the induced current? Change in magnetic flux. How can we change the magnetic flux? We can increase the magnetic flux, or we can decrease the magnetic flux. So increasing the magnetic flux or increasing the magnetic field, also we can do like this. Increasing the magnetic field or decreasing the magnetic field can induce induced current on the coil. So in the case of the increasing magnetic field, so then because the change is the increase, and if the applied magnetic field is from left to right, for example, give an example, in this case, induced magnetic field will oppose the applied magnetic field by making a direction from right to left. Assume that the applied magnetic field is from right to left, induced magnetic field opposes the applied magnetic field from left to right. But in the case of decreasing magnetic field, if the change is decreased, in this case, induced magnetic field will support the applied magnetic field. They will be in the same direction from right to left. If applied is from right to left, so induced will be from right to left. If applied is from if applied is from left to right, so induced will be from left to right. If applied is from right to left, induced will be from right to left again. So in the case of decreasing magnetic field, the induced applied magnetic field and induced magnetic field will be in the same direction. In the case of increasing magnetic flux, they will be in opposite directions. Now let's apply this to this one. For example, permanent magnet is receding and moving away from the solenoid. In this case, magnetic flux on the solenoid will decrease. So we are going to choose this condition, decreasing magnetic flux. So what is the applied magnetic field direction? It is from right to left. Yani this case. In this case, in this situation, induced magnetic field also must be from right to left. So it is also must be from right to left. So as you see, this is the direction magnetic field has entered from S pole and leaves from the M pole. So this must be S pole in this case. If this is M pole, this is S pole, that is M pole, use the right hand rule so you can understand that thumb points in the direction of the M pole. Curl forefinger is the electric current direction in the solenoid. Okay, so let's apply this to the following one. So right here the receding and moving away. So as you see, magnetic flux decreases here. Again, we are going to choose this one, but this time decreasing magnetic field is from left to right, yani this pace, this condition. So in this magnetic field also must be from left to right. So it must be from left to right. These two must be in the same direction. If it is like this, this must be N pole because magnetic field starts from N and goes to S. Then we are going to use the right handle and we will find the direction of the electric current on the coil and on the is approaching. If S is approaching, so in this case we are going to choose magnetic flux increasing magnetic field, but in which direction? From left to right, in this magnetic field must be from right to left, yani in that direction. If it is like this is S pole, that is N pole. Curl your forefinger, so electric current direction will be in this case, in this position, so electric current direction will be like this. So M pole, because points, the thumb points M pole, so curl forefinger is the electric current direction. So electric current will be from left to right on the resistor. Okay, so find the direction of the electric current is like this, and this current is like this. Conceptual challenge 1. A bar magnet is dropped towards the floor on which lies a large ring of conducting metal. This is a large ring. So the magnet's length and thus the poles of the magnet is parallel to the direction of the motion. So direction of the motion is down. So poles must be parallel, yani N and S or SN and. So disregarding a resistance, thus the magnet ring is fall downward. The ring move the same constant acceleration as freely falling body. While the permanent magnet approaches the loop or the coil, of course this coil will induce a current, and this induced current will produce an induced magnetic field. So induced magnetic field will polarize like this. If M pole is approaching, the over it will be M pole, below will be S pole. So if N and N faces each other, there will be a very slight repulsion between these two poles. However, because the mg is greater than that force, still it will accelerate, but with a small acceleration. So the magnet's acceleration will be slightly smaller because of the repulsive force between two M poles, and the magnetic field of this current opposes the field of the fallen object. So their directions are opposite. This induced field exerts an upward force on the magnet, reducing the magnet's net exertion downward. Suppose you are wearing a bracelet that is an unbroken ring of copper. If you walk briskly into a strong magnetic field while wearing the bracelet, how would you hold your wrist with respect to magnetic field in order to avoid inducing a current in the bracelet? How can you induce a bracelet is a loop? How can you induce a current on a loop? By changing the magnetic flux. But initially the bracelet is out of the magnetic field, so initial magnetic flux is 0. When you enter inside a magnetic field, final magnetic flux also must be 0. So in this case, there will be no change in magnetic flux. There will be no induced magnetic field. So there will be no induced current. So how can you make magnetic flux 0? If the ring is parallel to the magnetic field lines, and plane of the bracelet is parallel to magnetic field lines, there will be no lines crossing the area of the bracelet. So in this case, magnetic flux will be 0. No induced current will be on the bracelet. Upon entering and leaving the magnetic field, the plane of the bracelet must be parallel to the direction of the field. So there will be no change in magnetic flux through the ring of the copper, and there will be no induced current in this case. So Lenz's law is just about finding the direction of the electric current in this magnetic field, but by using the Faraday's law of electromagnetic induction, we find the magnitude of the induced current, E. So to calculate the magnitude of induced current E, we must use the Faraday's law of electromagnetic induction. So what is that law says? It says that induced EMF depends on rate of change in magnetic flux, and there must be a change in magnetic flux to induce any EMF, but this change must be faster. If it is faster, in this case, induced EMF increases, yani delta V over delta T. Also, if there are more than one loop, which is number of loop, so induced EMF also increases. So then, induced EMF, which is the average induced electromotive force in volt, N is the number of loops of the coil or the solenoid. Delta V is the change in magnetic flux through the loop, which is in Weber. So delta T is the time during which magnetic flux has changed in second. So delta V over delta T is also known as the time rate of change of the magnetic flux. So time rate of change of the magnetic flux, in fact, proportional to induced EMF. Yani if this time rate of change of magnetic flux is high, induced EMF is high. Now, let's solve a problem. It says a coil with 25 turns. 25 turns is number of turns, yani which is N, the chord N, 25 turns. A wire wrapped around a hollow tube. It's a cylinder with an area of 1.8 meters square. Yeah, and it's a kind of cylinder like this. We can draw it. So it has an area. This area is given as 1.8 meters square. So a uniform magnetic field is applied at right angle. Why is it set like this? Because if it is at right angle applied to the surface, magnetic flux is maximum. So you don't need to right angle for magnetic flux. Only A and B can be written in the equation. A uniform magnetic field is applied at right angle to the plane of the coil. If the field increases uniformly from 0 to 0.5, what's changing here? So according to magnetic flux equation, something must change. AB must change. But here, magnetic field is changing. So then, change in magnetic flux is equal to A times change in magnetic field. So magnetic field changes from 0 to 0.55. So change in magnetic field is 0.55. Increases because it's positive. In how many seconds? 85 seconds. Delta T is 0.85 seconds. Find the magnitude of the induced EMF in the coil. So we will find induced EMF in the coil by using Faraday's law of electromagnetic induction. Delta V over delta T negative times N. So this negative sign comes from the Lenz's law by the time. Don't forget this. Because the magnetic flux is A times P, but change in magnetic flux is A times delta P. Why? Because magnetic field is changing. So A delta B over delta T is multiplied by N is the equation for calculating induced magnetic field. So area is 1.8, change in magnetic field is 0.55, time is 0.85, number of turns is 25. When we multiply them, answer is 29 minus 29 volt. But question is asking find the magnitude of the induced magnetic field. When it says the magnitude, you never write it negative. For that, you should get the absolute value of this number. So in this case, 29 volt is the magnitude of the induced EMF. So question B, if the resistance of the coil is 25 ohm, find the magnitude of the induced current in the coil. So we are going to use the Ohm's law. So Ohm's law of current is equal to potential difference or induced EMF divided. Next question is, questions are very similar to each other. Just the thing you should know is that to find which one is increasing area or magnetic field. A single circular loop, N is equal to 1. With a radius of 22 centimeter, its radius is given to 0.22 meter. It's placed in uniform magnetic field with a string of 0.5 Tesla. So magnetic field is 0.5 Tesla. So that the plane of the coil is perpendicular to the magnetic field, so magnetic flux is maximum. The coil is pulled steadily out of the field in 25 seconds. So what's changing? Area inside the magnetic field is changing. So it's taken out 0.25 second. Delta T is equal to 0.25 second. Find the average induced EMF during this interval. Initially, because it's a circular loop, we should find the initial area inside the magnetic field by pi r squared. Pi is given, r is given. So 0.15 meters squared is the initial area inside the magnetic field. Complete it's inside. But area of the loop within the magnetic field still decreases and becomes 0 because we are pulling it out, as my hint is taken out. So the final area becomes 0 because it's complete outside the magnetic field. So thus a change in area will be negative. So final minus initial, negative 0.15 meters square. Now we use the Faraday's law of electromagnetic induction. So it is change in magnetic flux. This time area is changing. Delta A times P divided by delta T multiplied by N. So negative change in area is negative 0.15 times 0.15 divided by 0.25. So answer is 0.3 volt. In the next practice problem, magnetic flux is changed. The magnetic flux changing so that the magnetic field drops from 0.15, 1.6 to 0, so decreasing. Drops mean decrease. For that reason, change, because of the change in magnetic field, there's a change in magnetic flux. You should be careful because it's changing in decreasing. For change in magnetic field is negative 1.6. The rest are the same. You can do it on your own. Okay, question number 3. Right here, again magnetic field is changing, but initial magnetic field right now is 0.35 Tesla. So final magnetic field is negative 0.25 Tesla. So you should find change in magnetic field by subtracting initial from final. So then you should write it into your equation and you can calculate the result. Now next title is the self-induction. What is self-induction? Self means its own. So something its own can do something. It's called self. Electromagnetic induction is available only, initially we studied, there's a coil and a magnet. We move them relative to each other. Move away, you're getting closer, the magnet to the solenoid or the coil. We get the induced current on the coil. Second way, we are not going to use this. We are going to get it out. We are not going to use any magnet external source, but we are going to use a electric current source, a battery. And we are going to connect this battery to a solenoid or a coil. When in this case we can also get induced current or induced magnetic field. Why? Because initially no electric current flows on the coil, no magnetic field is produced, no magnetic flux through the coil. So initial magnetic flux is 0. When electric current is supplied with this blue sign, supplied, of course this solenoid will produce its own magnetic field from according to right hand rule. So it will be from right to left. Yani that those blue lines will show the applied magnetic field by the battery. So later, because magnetic flux increases from 0 to this number, so because the magnetic flux to the coil suddenly increases, according to Lenz's law, the coil itself produces another magnetic field that opposes the main magnetic field. So in this case, this magnetic field will be induced. These green lines, the direction of the induced magnetic field. So this opposite magnetic field, which is called induced magnetic, emerges from an opposing current on the coil. So if magnetic field is opposite current, there must be an induced current which is in the opposite direction of the supplied current. So this induced current is called self-induced current. So the net current on the coil will become supplied current minus induced current. Why? Because these two currents are in the opposite direction, but it takes very short time. It's also possible the creation of the EMF in a coil due to the change of the current. As you see, current increase from 0 to a number, or the coil itself is called self-induction. So you can, if you increase the electric current on a coil on a solenoid, the solenoid gives reaction to this increase and produces or reduces a current in opposite direction, which is called self-induced current. But if a similar effect can also be observed in the coil if the supplied current through the coil decreases by time, but in opposite manner. What's going to happen in this case? So if you decrease the electric current this time, the coil gives reaction to this decrease and induces a current in the same direction of the supplied current or applied magnetic field. So induced magnetic field is produced in the same direction of the main magnetic field. So this self-induced current circulates in the same direction of the main current in this case. Now we are going to get the equation for self-induction. Now in order to calculate the self-induced EMF, we are going to assume that a current I traverses a coil, moves in a coil, and produces a magnetic flux I, because there is a current, there is a magnetic field, there is a magnetic flux which crosses the coil. The change in current is delta I, produces a proportional change in delta phi. Delta phi and delta I proportional to each other. If you change the current, there will be a change in magnetic flux. Rate of change in the magnetic field will be proportional to rate of change in magnetic flux. If you multiply both sides with negative n, so it's also possible there will be no change in the proportionality. However, this proportionality can be made inequality by inserting a constant. So then this is Faraday's law of electromagnetic induction, E. will be equal to negative of some constant multiplied by delta I over delta T. That constant is known as the coefficient of self-induction. So then equation becomes negative L, which is the constant. From now on we are going to say coefficient of self-induction, delta I over delta T. Now according to change in the electric current in a coil, we can also find the induced EMF in this coil. So L is measured in volts times second divided by ampere. It's not so difficult, just you are going to cross multiply this and you are going to let L alone. L is equal to negative E divided by delta I over delta T. So volt divided by, when you turn it upside down, it becomes like this, negative E delta T divided by delta I. So unit of in coefficient of self-induction is volt times second divided by ampere, or simply it's called Henry. Questions are very easy. If the electric current grows in a circuit from 0 to 10, so change in electric current is plus 10. From 0 to 10, it's plus 10. During how many seconds? 0.5, delta T is 0.1 second. If the coefficient of self-induction L of the circuit is 0.02 Henry, L is equal to 0.02 Henry, calculate induced EMF, minus L delta I over delta T, minus L is 0.02, delta I is final minus initial divided by delta T, answer is negative 2 volt. So coefficient of self-induction depends on the geometrical property of the coil or solenoid. Now we are going to find how to calculate the coefficient of self-induction for solenoid. So these two equations are defining the same thing. One of them is according to Faraday's law of electromagnetic induction. So according to change in magnetic flux, we calculate the induced EMF. In the second one, we calculate the induced EMF according to change in electric current. When we make them equal, so N times delta phi, L times delta I, or this equation can be written. If the current is kept constant, magnetic flux also kept constant. So magnetic flux is area times magnetic field. We know that through the solenoid. Through the solenoid, magnetic field is mu I N over L. So when you rearrange the equation, you are going to get the L for solenoid, which is mu N squared A over L. So this is coefficient of how to calculate coefficient of self-induction of a solenoid. L is the coefficient of self-induction of a solenoid, only for solenoid, specific only for solenoid. So which one leads to a higher increase in the coefficient of self-induction of the solenoid? Doubling the number of turns, doubling cross-section area. Doubling cross-section area increases the self-induction by 2, but doubling N increases by 4 because it's squared. Now, another question, sample problem. It says an air solenoid of length 10 cm and cross-section area 25 cm square and 400 turns is traversed by a current of 4 ampere. So length is 0.1, 10 cm, 0.1. Area is 25 cm square, 0.0025 meter square. Number of turns is 400. Current is given as 4 ampere. Current, calculate the magnetic flux which crosses the solenoid. Calculating magnetic flux is easy because field is magnetic field multiplied by area. Magnetic field for a solenoid is mu I N over L multiplied by area. Mu is this 4 pi times 10 to the power minus 7. N is 400. Current is 4 ampere. L is 0.1. Area is 0.0025. So magnetic flux through the solenoid is 5 times 10 to the power minus 5 Tesla times meter square or Weber. So B, if the current is reversed during 0.1 second, so delta T is the 0.1 second, calculate the induced EMF. When the current is reversed, final magnetic flux becomes negative. If initially it's positive 5 times 10 to the power minus 5, so final will be negative 5 times 10 to the power minus 5. So as you see, magnetic flux is changing. Simply use Faraday's law of electromagnetic induction and calculate induced EMF. Yani negative delta V over delta T. Final magnetic flux is negative 5 times 10 to the power minus 5. Initially it's 5 times 10 to the power minus 5 divided by time multiplied by number of turns. So it is 0.4 volt. The inside story is the next title. It's about electric guitar pickup. In fact, electric guitar pickup has 3 main components. One of them is the permanent magnet. So this is a permanent magnet with N pole and S pole. A coil is wrapped over the permanent magnet. This is a coil. And also a string is needed, but this string is a special spring. So it's a ferromagnetic material which can be magnetized by this permanent magnet. If this is N pole, that side S, this is N. Why is it like this? When you hit the string is starting to vibrate. As a result of this vibration, string comes closer to the coil, moves away from the coil, closer, more away. So induces a current on the coil. So this current will be an alternating current. According to frequency of the vibration and the amplitude of the vibration, this current's vibration frequency and amplitude also changes. You are going to send it amplifier because this current is very low value of current, 0.1, 0.005, something like this. To amplify it, you can increase the power, and after that send it to speaker. We are going to get the same sound as the guitar from the speaker. This is the inside story. And next and last title about this section is eddy currents. In fact, eddy currents are no different than the induced current. Induced current is produced in a loop. Eddy current is produced on a rigid object. So when a conducting bar moves in a magnetic field, the electromagnetic induction phenomenon that rises due to the change in magnetic flux, as you see, it's the same condition of the change in induced current, leads an induced current, induced circular current within the material. These currents are called eddy currents. So eddy currents are used in furnaces, carburetor systems, and detecting metals. These three things are important. Most probably they are going to ask this question in one of the ministry exam. Section of questions. Question number 1. A circular current loop made of flexible wire is located in a magnetic field. Describe 3 waves and an EMF can be induced. In fact, we know that you are going to change the magnetic flux. You can change the magnetic flux by 3 waves: area, magnetic field, or location or orientation. By changing the magnetic field strength, B. By moving the loop in or out of the magnetic field, A. By changing the orientation of the loop with respect to the magnetic field, theta. Question number 2. A bar magnet is positioned near a coil of wire as shown to the right. What is the direction of the current in the resistor when the magnet is moved to the left as in A, or to the right as in B? So if it moves to left as in A, so because N pole is receding, moving away, this becomes S. That becomes N. According to that, you can find your thumb will point in the direction of the N pole. So curled forefinger is the electric current direction on the loop. So electric current direction on the loop will be like this. Follow the line, follow the wire, so you will see that electric current is from left to right on the resistor. In part B, electric current will be opposite because poles will change. This will be N, that will be S. Electric current direction also will change. Question number 3. A 256 turn coil, so number of turns is 256, with cross-section area of 0.0025 meters square. So cross-section area is this. Placed in uniform external magnetic field of strength 0.25, so magnetic field is 0.25 Tesla, so that the plane of the coil is perpendicular to the magnetic field, so maximum magnetic flux is produced. The coil is pulled steadily out of the field. When we pull the coil out of the field, which means area of the coil inside the magnetic field changes. For that reason, area is changing. Delta A is negative 0.025. In how many seconds? 0.75 seconds. Calculate the induced EMF during this time interval. So induced EMF can be calculated delta V over delta T times N. Because area is changing, delta A times P divided by delta T times N. Change in area is negative 0.0025 multiplied by magnetic field 0.25 divided by time delta 0.75 multiplied by number of turns 256. Answer is 0.21 volt. So in fact, question number 4 is exactly the same as the electric guitar strings. In fact, it defines how electric guitar strings work. It says an electric guitar strings are made of ferromagnetic materials, yet important ferromagnetic materials that can be magnetized. The string lies closed over and perpendicular to the coil of the wire. Inside the coil, there are permanent magnets that magnetize the segments of the strings overhead. Using this arrangement, explain how the vibration of the plucked string produces an electrical signal at the same frequency of the vibration of the string. Because according to this explanation I made, we said that when the guitar string starts to vibrate, it induces a current on the coil. This current will have the same frequency of the vibration of the guitar string, also the same amplitude of the vibration of the guitar string.